Hello everyone, we are at the topic of transistor amplifiers, and today we are going to see how we can characterize these amplifiers. So at the beginning of the course, we talked about how dividing the circuit into building blocks can be used to simplify the analysis and the design of more complicated circuits. So a typical analog circuit contains a load, this one, and a source, which are two terminal networks, and several two-port networks. Here we would like to characterize the performance of an amplifier as a circuit building block. So since transistors are voltage amplifiers, we are going to use the well-defined voltage amplifier model to characterize our amplifiers and use them as a circuit building block. So this is the voltage amplifier model that you saw before. The parameters of the voltage amplifier model are open loop gain. We're going to show that with A sub VO, and it's defined as output voltage Vout divided by Vi when there is no load connected to the output or when the load resistance is infinity. The input resistance is defined as Vi divided by II, the current that enters the voltage amplifier, and the output resistance of the amplifier is defined as a negative of Vout divided by Iout when there is no voltage applied to the input, when the Vi is equal to 0. So we're going to use the voltage amplifier model to characterize our transistor amplifiers and use them as two-port networks. So the total voltage gain of the circuit, we're going to show that with A is defined as Vout divided by V signal. This V signal and R signal might be the function generator. For example, V signal is the voltage at the output of function generator, and R signal is the internal resistance of that function generator. Or it might be the output from another amplifier circuit. The voltage gain of the amplifier is defined as AV, and it's defined as Vout over Vi regardless of V signal. So the total gain of the circuit, voltage gain of the circuit, is shown by A. It's Vout over V signal, and voltage gain of the amplifier itself is Vout over Vi. The other term is open loop voltage gain, which is defined as Vout over Vi when there is no load. So the overall gain is defined as Vout over V signal. It can be calculated by finding Vi over V signal, multiplying the result by Vout over Vi. I know that Vout over Vi is AV, and this is a simple voltage divider network here. Vi, the voltage across this input resistance, is Ri divided by Ri plus R signal multiplied by V signal. So Vi over V signal is Ri divided by Ri plus R signal. On the other hand, at the output side, AV, or the voltage gain of amplifier, is defined as Vout over Vi. This is again a voltage divider circuit. Vout is RL divided by RL plus RO, and that's multiplied by this voltage here, AV naught multiplied by Vi. So Vout over Vi is RL divided by RL plus Rout multiplied by the open loop gain. So we studied the effect of output resistance and input resistance of a voltage amplifier at the beginning of this course, and there you saw that we would like to have a large input resistance for our amplifiers compared to the signal resistance, because if Ri is in this equation, if Ri is much larger than our signal, then Vi and V signal are almost the same. When Ri is equal to the output resistance of the voltage source, for example, then Vi is going to be only half of the signal that we are connecting to our amplifier. And if Ri is much smaller than our signal, then there is practically nothing applied to the input of our transistor. On the other hand, for the load side, for the output side, and we would like to have a small R out for our transistor or for our voltage amplifier, because if R out is much smaller than the load resistor, then AV is going to be almost equal to open loop gain, and if R out is equal to the load resistor, then the voltage gain is equal to half of the open loop voltage gain. And on the other hand, if R out is much greater than the load resistance, there is almost no gain at the output of this transistor amplifier. So let's take a look at the whole process of analyzing amplifier circuits and review what we have done so far. So this is in the red box. There's an amplifier circuit that the circuit contains load resistor, the signal with its internal resistance connected to the amplifier, and I have a MOSFET amplifier. So to analyze the circuit, we're going to start by analyzing the bias circuit or the DC circuit. That means we're going to assume the capacitor, we're going to open the capacitors, we're going to zero out the signal voltage and currents, and if you do that, this is your bias circuit for the given amplifier, this whole amplifier circuit. So this is the bias one. This is bias plus signal, the whole thing. And then after finding the bias parameters, meaning that after you found ID and VD, VDS, VD and VS and VG, you're ready for the small signal analysis. So we're going to replace this MOSFET with its small signal model, which is here in this blue box, and then we're going to zero out the DC voltage sources and DC current sources, and capacitors, we're going to assume that the capacitors are short in the signal circuit. Then you're going to end up with this circuit in the blue box. Okay, so this is the signal circuit or signal equivalent circuit for the circuit in the red box. Now, if I characterize my voltage amplifier or the MOSFET amplifier by calculating its input resistance, its open loop gain, and output resistance, then I can replace this whole circuit from here to here with this the circuit inside this box. What I'm doing is representing the amplifier circuit as a building block, and doing so has the benefit of simplifying the calculation. So I'm keeping load resistance and anything from the signal, which is the Thevenin equivalent of the signal source, V signal and R signal, separate from the transistor circuit. And if you do so, you can simplify the calculations. Here is an example of how it might help you for analyzing the rather more complicated circuits. So look at this, the given circuit. It's a cascade of two amplifiers, and instead of analyzing this circuit, the whole entire circuit from scratch, you can find the model of the circuit for this transistor 1, and it's a characterized version for transistor 2. It's the model for transistor 2. This is for transistor 2, and this box is for transistor 1. The only thing I did was finding AB node, analyzing them separately, finding AB node for transistor 1 and R out 1 for transistor 1, and then finding AB node for transistor 2 and R out for transistor 2, and then using their voltage amplifier model in the building block representation of the whole circuit, keeping RL separately and R signal and B signal separately. Then I can easily calculate the voltage gain or the total voltage gain or the amplified voltage gain, or study the effect of RL on the gain of this amplifier, or the effect of R signal on the gain of this amplifier. So for example, I can write the gain equation, V out over V signal, as the given equation, because I know that V out over V signal is equal to V out over VI VI2 multiplied by VI2 divided by VI1 multiplied by VI1 divided by V signal. So I use this equation to derive this provided gain equation. So that helps to simplify the calculations.